Hi everyone and welcome back to another lab. In this video, we will configure and verify Rapid Per-VLAN spanning tree protocol or RPVST+. I will start by briefly explaining what spanning tree protocol is, and then I will cover the different types of spanning tree and the spanning tree election process. Next, I will outline the lab objectives, review the lab topology and tables, and then walk through the lab tasks, and finally I will guide you through the solution step by step. By the end of this lab, you would have explored the Per-VLAN spanning tree protocol and gained a better understanding of how PVST and RPVST Plus work and how they can be used to optimize network performance and stability. So the main purpose of spanning tree protocol is to prevent loops in Ethernet networks. So SDP will make sure that there is only one path between any two network nodes. When switches are powered on or interconnected, they exchange something called Bridge Protocol Data Units or BBDUs frames. BBDUs contain information about the switch, such as its bridge ID or BID, the priority, and the cost of reaching the root bridge. All switches in the network participate in an election process to determine the root bridge, which serves as the central point of the spanning tree topology. The root bridge is the switch with the lowest bridge ID, which is a combination of the priority and the MAC address. If the priorities are the same, the switch with the lowest MAC address becomes the root bridge. Once the root bridge is elected, each non-root switch selects one of its ports as the root port. This port offers the lowest path cost to the root bridge, and each LAN segment has one designated port responsible for forwarding traffic to and from that segment. Initially, all ports on non-root switches are in a blocking state, meaning they do not forward traffic but listen to BBDUs to determine the best path. SDP calculates the best path to the root bridge for each switch and transitions certain ports from blocking to forwarding states. And there is only one active path, as mentioned earlier, which is going to be in the forwarding state between any two switches. This will prevent loops that can cause broadcast storm and network instability. Redundant paths are kept in a blocking state until a primary path fails. If the primary path fails, then SDP recalculates and activates the redundant path to restore connectivity. BBDUs are continuously exchanged between switches to monitor network changes and adapt the spanning tree topology accordingly. When there is network change occur, for instance link failure or topology change, switches sends out BBDUs to inform others, triggering recalculations of the spanning tree. Now that we covered briefly what is spanning tree protocol, now let's talk quickly about the Per-VLAN spanning tree protocol. So PVST is a protocol that was developed by Cisco, which allows a separate spanning tree instance for each VLAN in a network. Unlike standard or traditional STP, which maintains a single spanning tree for the entire network. In Per-VLAN spanning tree, each VLAN can have a different root bridge, enabling more granular control over the network topology, and that helps in load balancing and sharing and optimizing traffic flow. Also, in Per-VLAN spanning tree, each VLAN transmits its own BBDUs. These BBDUs contain information about the VLAN specific topology, root bridge, and path costs. BBDUs are sent out at regular intervals, every 2 seconds by default, to maintain the spanning tree topology. Each VLAN holds its own election for the root bridge, and the switch with the lowest bridge ID, which is a combination of the priority value as well as the MAC address, becomes the root bridge for that VLAN. By default, all switches have the same priority, 32,768. But network administrators can manually set the priority to influence the root bridge election, which we will do in this lab. Just like in standard STP protocol, each port can assume roles such as root port or designated port or non-designated port. Path cost is calculated based on the bandwidth of the links, and the lower the path cost, the more preferred the path is. Each VLAN independently calculates path costs to determine the best path to the root bridge for that particular VLAN. Okay, now with that being said, let's move into the different types of spanning tree. And the first one that we see is the classic spanning tree protocol, the traditional one. This is the original spanning tree protocol. And the primary function of this spanning tree is to prevent network loops by creating a loop-free logical topology from physical topology and that could contain loops. Although STP is effective at preventing loops, it converges really slow, taking anywhere between 30 to 50 seconds to transition from the blocking state to the forwarding state, which can be problematic for the modern networks requiring high availability. The second type of spanning tree is the Per-VLAN spanning tree protocol, or PVST, and it is Cisco's proprietary Per-VLAN spanning tree protocol enhances STP by allowing a separate instance of STP to run for each VLAN in the network. This approach provides several advantages, such as load balancing traffic by configuring different route bridge for different VLANs and therefore utilizing redundant links more effectively. PVST also provide better control over network resources and can improve network stability and performance. However, running multiple spanning tree instances increases the CPU and memory requirements on switches, which can be a limitation in large-scale networks. The next type of spanning tree is the Rapid Spanning Tree Protocol, or RSTP, and the main purpose of this protocol is to address the slow convergence issue of STP. The IEEE developed the Rapid Spanning Tree Protocol, and it improves the conversions type by introducing new port rules and states, reducing the time it takes for the network to adapt to topology changes. Instead of the multiple state in STP, RSTP simplifies this to three port states, which are the discarding, the learning, and the forwarding states. In addition to that, RSTP introduces the concept of edge ports, which can transition immediately to the forwarding state, and introduces rapid transition mechanism for point-to-point links. These enhancements make RSTP more suitable for modern networks that demand quick recovery from failures. The next type is the Rapid Per-VLAN Spanning Tree Protocol, or Per-VLAN Rapid Spanning Tree Protocol. Cisco extended the benefits of RSTP to Per-VLAN implementations with Per-VLAN Rapid Spanning Tree Protocol. Similar to PVST, Rapid PVST runs a separate instance of RSTP for each VLAN, combining the fast convergence benefits of RSTP with the Per-VLAN flexibility of PVST. This allows for efficient use of network resources and load balancing across different VLANs, while also ensuring rapid recovery from topology changes. And finally, Rapid Per-VLAN Spanning Tree Protocol is widely used in Cisco networks for its robustness and efficiency. And the final type that we can see is the Multiple Spanning Tree Protocol, or MSTP. And this protocol is primarily focused to address the scalability issue associated with running multiple spanning tree instances. The IEEE developed the Multiple Spanning Tree Protocol, standardized as IEEE 802.1s, and this protocol allows multiple VLANs to be mapped to a single spanning tree instances. This way, reducing the number of spanning tree instances required and therefore saving CPU and memory resources on switches. Each MSTP region can have multiple MST instances, with each instance handling multiple VLANs. MSTP provides the benefits of load balancing and fast convergence while being more scalable for large networks with the numerous of VLANs. Next, let's move into the spanning tree protocol election process, which is essential for ensuring a loop-free and efficient network topology in Ethernet networks. This process begins with each switch in the network participates in an election to determine the route bridge, which serves as the central reference point for all path calculation. The election is based on the bridge ID, which is a unique identifier for each switch, and the switch with the lowest BID is elected as the root bridge. In the initial phase of the election process, each switch sends out bridge protocol data units containing its BID to all other switches in the network. A BBDU is a type of network message that includes information about the sending switch's BID and the route path cost to reach the root bridge. The switches then compare their BIDs with those received from neighboring switches. If a switch receives a BBDU with a lower BID than its own, it updates its BBDU to reflect the lower BID and starts forwarding this information to other switches. This comparison process continues until all switches acknowledge the switch with the lowest BID as the root bridge. Once the root bridge is elected, the protocol moves into the rule assignment phase. Each switch must determine the rules of its ports to maintain a loop-free topology. Ports are classified into different rules. We can see the root ports, designated ports, and non-designated ports, or the blocked ports. Each switch has only one root port. The designated ports are selected on each network segment to provide the best path to the root bridge and are responsible for forwarding frames. Finally, the non-designated ports or blocked ports do not forward frames and effectively prevent network loops. Throughout the network, the root bridge sends out regular BBDUs to maintain its status and manage the network paths. These BBDUs propagate through the network, allowing switches to update their port rules as needed. If the network topology changes, such as when a link fails or a new switch is added, the STP election process is reinitiated to adapt to the new changes and ensure continued loop-free operation. This dynamic adjustment capability is crucial for maintaining network stability and performance. With regards to the lab topology, we have a couple of VLANs. We can see VLAN 10 and VLAN 20. We can see that PC1 and PC3 as well as server 1 are part of VLAN 10. And on the other hand, we can see that PC2, PC4 and server 2 are part of VLAN 20. There are 3 switches in the topology, as you can see that in the screen, that are interconnected with each other. So switch 1 is interconnected with switch 2 via gig ethernet 01, and switch 2 is connected to switch 3 via gig ethernet 02, and finally switch 3 is connected to switch 1 via both interfaces fast ethernet 010 and fast ethernet 011. And the objective of this lab is to analyze and verify the default spanning tree protocol that is used on a Cisco switch, and we will also do some spanning tree modification to enforce a switch to become the root bridge, for example, for a particular VLAN, and configure Rapid Per-VLAN spanning tree protocol. So regarding the lab tables, the first table that we are going to tackle is the switch VLAN table, and that table presents details regarding devices, interface configuration, and associated VLANs. You can see the device name is the column lists the names of the network device. The interface ID is the column displays the unique identifiers of the interfaces on the respective device, and then the interface mode, which indicates the operation mode of each interface. For instance, fast ethernet 01 will operate in access mode and it will be part of VLAN 10. Fast ethernet 02 will be also operating as in access mode and will be part of VLAN 20, whereas gig ethernet 01 as well as fast ethernet 010 and fast ethernet 011 on switch 1, all these interfaces, all these 3 interfaces will operate in trunk mode and will only allow VLANs 10 and 20. Finally, the end host IPv4 address table, and this is just for your information. In this lab, we've already configured the end host prior to the lab with the information you see on this table. For instance, PC1 will have 192.168.10.100 with the /24 subnet mask, and it will be part of VLAN 10. And PC2, we can see that is going to be part of the 192.168.20.100 and is also going to have /24 as the subnet mask and is part of VLAN 20. Next, let's move into the lab task. And here in this lab, we are going to tackle the first task, which is going to verify the current configuration. We're gonna check the VLAN database, make sure that each interface resides in the appropriate VLAN according to the table that we just discussed. We're gonna make sure that there is connectivity between each PC that are part of the same VLAN. And then once we have done that, we are going then to move into the second step. And the second step is going to determine the type of spanning tree that is used by default on Cisco switches. Then we move to step 3, and this is where we're going to discover and verify the root bridge for both VLANs, VLAN 10 and VLAN 20. We're going to answer a few questions, or we're going to go through a few questions to understand and analyze the output of the spanning tree from the switch. We then move into step 4, where we're going to force switch 3 to become the root bridge for VLAN 20, what command we need to use, and how we're going to verify that. We're going to tackle this in task 4. And then next, we're going to move to step number 5, where we're going to configure PVST plus mode on each switch. And once we have done that, we will verify our configuration. And then we're going to move to step 6, where we're going to verify that PC1 is still able to ping PC3 and PC2 is still able to ping PC4, and PC1 and PC3 are able to ping each server 1 and server 2. Next, we're going to save the configuration. Once we have verified that each PC is able to ping the other PC and the server within the same VLAN, we can then go ahead and save our configuration. If the ping, however, fails for some reason, we can follow these steps methodically to troubleshoot the problem, isolate it, and try to fix it here and there. Okay, this is the moment where I ask you to pause the video and give this a go yourself to test your knowledge and skills. So I added the lab document in the video description so that you can download it and practice it at your own pace. I have also included a couple of packet tracer labs for you to download. You will find a pre and a post version of that lab. The pre-lab is for those who wants the lab ready to go and tackle all tasks, and the post lab is for those who wants the full lab solution. So what I'm going to do, I'm going to tackle the first task, which is going to check the current configuration on each switch, and then we're going to initiate some pings between PC1 and PC3, PC2 to PC4, and then PC3 to server 1 and PC4 to server 2. So first of all, first things first, let's check the current configuration on each switch. So I'm going to log into switch 1. And the first command that I'm going to use is the show VLAN brief. And here we can see that there are current 2 VLANs that have been configured, and each interface is configured with the appropriate VLAN. So we can see Fast Ethernet 01, which is connected to PC1, is part of the VLAN 10, and PC2 or Fast Ethernet 02 is connected to PC2, and that is part of VLAN 20. Next, what I can do, I can issue the show interface status. And here, this confirms that this interface, Fast Ethernet 01, is linked to PC1. Fast Ethernet 02 is linked to PC2. PC1 is part of VLAN 10. PC2 is part of VLAN 20. We can see that Fast Ethernet 010, Fast Ethernet 011, both of these links are connected to switch 3, and both are operating in trunk mode. We can also see that Gig Ethernet 01 is linked to switch 2 and currently is also operating in trunk mode. Next, let's examine the trunks. So I'm going to say show interfaces trunk. We can see that currently there are 3 trunk interfaces, and the current VLANs that are allowed and the active VLANs are 10 and 20. So let's do the same thing on switch 2. So again, we can see 2 VLANs have been created and assigned to the appropriate interfaces. And I'm going to issue the show interfaces status. Again, we can see 4 links. 2 links are connected to the end hosts, and each link or each interface is associated with the appropriate VLAN. And also similarly with the links that are connected to switch 1 and switch 3, Gig Ethernet 01 is connected to switch 1, Gig Ethernet 02 is connected to switch 3. Both of these interfaces or both of these links are trunks. Let's examine the trunks interfaces. And here we can see that we have two trunks, Gig Ethernet 01 and 02, and the current allowed and active VLANs are 10 and 20. Finally, let's do the same thing on switch 3. So the VLANs have been created and each interface resides in the appropriate VLAN, as you can see on the screen. Next, let's issue the show interface status. Fast Ethernet 01 and Fast Ethernet 02 are links to the end hosts. The Fast Ethernet 010 and Fast Ethernet 011 are links to going back to switch 1, and you can see that they are operating in trunk mode. And finally, Gig Ethernet 02, which is connected to switch 2, is also operating in trunk mode. Let's check the trunk interfaces. You can see that we have 3 trunks as we speak, and the current allowed and active VLANs are 20 and 10. Next, let's initiate some ping tests. So I'm going to go back to the topology and go to PC1, go to test stop, and then command prompt. And from here, I would issue ping 192.168.10.101 to ping PC3. And that is successful. Let's try to ping the server 192.168.10.200. I also have reachability, which is good. Now let's do the same thing on PC2. So I'm going to say 192 or ping 192.168.20.101. And there is connectivity. Next, let's ping server 2. So I'm going to say 192 or ping 192.168.20.200. And there is also reachability. Next, let's jump into step 2, where we're going to find out what is the current STP mode that is being used on Cisco switches by default. So I'm going to go back to switch 1. And from here, I will issue this command, show spanning tree summary. And here it tells you that the current spanning tree mode is per-VLANing spanning tree. Let's examine switch 2. And is also the same. So you can see switch is in PVST mode. Finally, let's do the same thing on switch 3. So show spanning tree sum or summary, and we get the same output as well. Next, let's jump into task 3, where we're gonna issue the appropriate command to determine the root bridge for the current topology for VLAN 10 and VLAN 20. So I will start with switch 1. So from here, I will issue this command, show spanning tree VLAN 10. And in here, you can see that we have an output for spanning tree VLAN 10, and it's divided into multiple sections. So the first section, which is what I'm highlighting on the screen, is related to the root bridge. And right now, you can see that this output is pretty much identical to this output, and the reason being is because switch 1 is the root bridge for VLAN 10. And what you see on the screen is the root ID. The root ID is a combination of the priority value, which is 32,778, and I understand that the default is 32,768, but we need to understand that the VLAN ID gets added into the default value. So the total of that, or the sum of that, becomes the current value that you see on the screen. This is the current MAC address of the root bridge. And if you compare this MAC address with this MAC address, you will find it identical. And the reason being is because switch 1 is the actual root bridge. And as we mentioned, this top section of the output is actually related to the root bridge. And you can see that there is a message here that explicitly tells you that this is the root bridge for VLAN 10. Let's do the same thing for VLAN 20. So I'm going to say show spanning tree VLAN 20. And we get similar output because, as mentioned earlier, the default of the priority value is 32,768. And we need to add the VLAN ID, which is going to cause it to pump into 32,788. The MAC address is going to be the same, obviously. And if you look at the port or interfaces, you can see that all interfaces are in the forwarding state. So here, this is FWD, which stands for forwarding, and all of these ports roles are designated ports. Let's issue the same command on switch 2 and switch 3. So I'll go back to switch 2 and I'll say show spanning tree VLAN 10. And you can see here the first section of the output is related to the root bridge. You can see that this is the current priority for the root bridge. This is the MAC address for the root bridge. And also it highlights the port that is used to get to the root bridge. And the section below here, this is related to the local switch. So you can see that the local switch has a priority of 32,778, which is exactly matches the current priority for the root bridge. And you can see this is the MAC address for the local switch, and you can see that is not the same or is not similar to the root bridge. Okay, so let's move forward with the output from the command. And here in this section, we can see that we have a small table that defines each interface ID, the role of each interface and the status, as well as the cost and the priority ID and the type of these interfaces. So the first interface that we see on the screen is the fast Ethernet 01, and the current role for this port is the designated port. The current status for this interface is forwarding, and the current cost in order for this interface to reach the root bridge is 19, which is less preferred in comparison to Gig Ethernet 02 and 01. And here you can see this is the priority number, and it combines two pieces of information, the port priority and the port number. This combination is used in the spanning tree protocol to make decisions about which port to select as root port and designated port. And finally, the type of the interface, and you can see that this is P2P, which stands for point to point. If we move forward, you can see that Gig Ethernet 02. Gig Ethernet 02 is also designated port and in the forwarding state, and the current cost to get to the switch 1 or to the root bridge is 4, and the current priority number is 1200.26. Again, the type is point to point, and finally is the Gig Ethernet 01. So you can see that Gig Ethernet 01 is a root port, and it means that this is the primary path to the root bridge for the switch and to forward traffic towards the root bridge. Currently is in the forwarding state, and the current cost is 4, and the priority number is 128.25. So you can see that this one is lower than the Gig Ethernet 01. Therefore, this interface becomes the root port. Let's jump into switch 3 and issue the same command. So I'm going to say show spanning tree VLAN 10. And we know that spanning tree for VLAN 10 is similar to VLAN 20. So with that being said, we can see here from the top section of the output, this is the information related to the root bridge. The current cost to get to the root bridge is actually 8, and you can go via Gig Ethernet 02. So the root port here you can see is Gig Ethernet 02 as showing from the output above. And as mentioned before, this is the information related to the local switch. And then finally, we can see that the interface information and the rule port for each interface, the status, the cost, and the priority number, and the type of each interface. So if we look at the fast Ethernet 01 is a designated port, and the current status is in the forwarding state, and the current cost to get to the root bridge is 19. The current priority number is 128.1. The next two ports, which are fast Ethernet 010 and fast Ethernet 011, and the current rule for these two ports is the alternate ports, which means that these two ports are used as an alternative path to the root bridge. If the primary path to the root bridge have failed, then one of these two links will become the root bridge. You can see that the current cost for these two interfaces is 19. The current priority number is 128.10 for Fast Ethernet 010 and 128.11 for Fast Ethernet 011. Finally, the Gig Ethernet 02 is the root port and is in the forwarding state, and the current cost for this interface is 4. However, if you look at the cost here to get to the root bridge is 8, and the reason being is because we know that Gig Ethernet 02 is connected to switch 2, and that link cost is 4, and then switch 2 is then connected to switch 1, which is connected via Gig Ethernet 01, which has a cost of 4. So if we then add 4 plus 4, that will give us 8, which is what you see on the screen here. Okay, so what we're going to do next, we're going to force switch 3 to become the root bridge for VLAN 20. So we haven't actually seen the spanning tree for VLAN 20. Let's do that quickly. So show spanning tree VLAN 20, and here you can see that the current root bridge is still switch 1 because it has this MAC address. So what we're going to do, we're going to force switch 3 to become the root bridge for VLAN 20. So what I'm going to do, I'm going to go back to global config mode, and then from here I'm going to say spanning tree VLAN 20 and then priority. We question mark that, and then here we need to include or configure the bridge priority. And it does tell you here that it has to be an increment of 4096. So we're going to say 8192. Now we would need to wait for a few seconds until the spanning tree converges. And then let's issue the show spanning tree VLAN 20. And right now you can see that the status of each interface is still learning. And right now you can see that all the interfaces are in the designated role and all of the interfaces in the forwarding state. Right now you can see that the switch 3 is the root bridge for VLAN 20, and this is the MAC address for switch 3. So if we just remember this MAC address, because I'm going to go back to switch 1, and I'm going to issue show spanning tree VLAN 20, and you can see that the root bridge for VLAN 20 has this MAC address, and the current priority is 8212. And this is the MAC address which matches switch 3's MAC address. So if I go back to switch 3, just do this, you can see that this MAC address matches this MAC address on switch 3. So another thing that I wanted to show you as well is if you don't want to use a priority value to force switch 3 to be the root bridge for VLAN 20, what we can do is we can issue this command. So I'm going to go back to global config, and from there I would say spanning tree VLAN 20. And then if you hit the question mark, you'll see the content sensitive help that would give you the options for this command. And right now we can set the priority value, and we have used this command. However, the other alternative option that you can do is you can use the root option. So you would say root, and then if you question mark that, you can then define it as the primary or the secondary root bridge. So right now we can see it's primary, but we don't need to issue this command since we already forced switch 3 for spanning tree VLAN 20 to be the root bridge, and we already verified that. So I'm going to cancel this. And next, let's move into step 5, where we're going to configure Per-VLAN spanning tree plus. So in order for us to do that, I will actually go back to switch 1, go to config global, and from here I would say spanning tree mode and then question mark that, and you can see the different options that you can find from the content sensitive help. And right now, to fulfill the requirements of the lab, we would need to use the Rapid Per-VLAN spanning tree, or Rapid-PVST command. And we would hit enter, we hit end, and then let's do the same thing for switch 2 and switch 3. And finally switch 3. And let's perform some verification and in-flight checks. So I'm going to say show spanning tree sum. And here you can see that the current mode has changed from PVST to Rapid PVST mode. Let's do the same thing for switch 2. And here we get the same output. And finally on switch 3 we get the same output as well. So let's just verify the spanning tree protocol on each switch once more, just to make sure that everything is as expected. So show VLAN, or sorry, show spanning tree VLAN 10. You can see this is the root bridge for VLAN 10. And if I issue the same command for VLAN 20, we can see that the root bridge is switch 3 based on this output. So if I go to switch 2 and issue the same thing, so show spanning tree VLAN 10. So the root bridge for VLAN 10 is switch 1 based on this output. And if I issued the same command but with VLAN 20, we can see that the root bridge for VLAN 20 is switch 3 because of this output. Okay, so with that being said, let's go back to our topology and go back to PC1 and start to reinitiate the same command. And we still have connectivity. Let's do the same thing for server 1. And there is also connectivity in there. Let's go to PC4, let's say. And I'm gonna go to command prompt and I'm going to ping 192.168.20.200. This is server 2. And I'm still able to reach server 2. And if I do the same thing but for PC2, and I have got reachability as well. So now that we have reachability between each nodes within the same VLAN, what we can do, we can go ahead and then save the configuration. So I'm going to go back to switch 1 and I will issue WR or copy running startup config and do the same thing here. And finally on switch 3. Okay, so that's it folks for this video. If you found this video helpful, please don't forget to give it a thumbs up. And if you haven't already, please hit that subscribe button and turn on notifications so you never miss our future tutorials and tech insights. If you have any questions, comments, feel free to drop a comment below. I read all your comments and I'm here to assist you. Remember, consistency and hands-on practice are key to success. So stay curious, stay inspired, and until next time, peace.